Hello, everybody. Today we're going to be talking about how tensor calculus can be used to analyze a bridge. So let's first define some terms to make sure you don't lose the main points that we discuss in this video. So, for example, yeah, first is strain. Strain is, for example, if we make a little cube, strain is when a thing or material is being stretched out. Think of like a strain on like your body, for example, like having a hamstring strain. It means that you stretched your hamstring too far. So that's what the strain refers to here. The stress, this is how much force, in this case, the block experiences. So as you can see up here in this diagram, our green arrows, that's going to be the stress. So that's going to be what is on it. For example, if there was like a ball or something on top of a box, the box would be experiencing stress from the ball. And then the shear, this is simply talking about our deformation of the shape as we stretch it. So as we stretch a cube, it's going to look more like, it's going to look kind of a little bit wonky, a little bit, but it is going to change shape, obviously, a little bit. But as we can see here, because of some of the stress we're putting on it and us straining it, that it's going to shear. So for our first point of analysis, what we're going to look at is we're going to look at this bridge, and we're going to say that the cable is modeled by this right here, where h of x is equal to this cosine curve. And then here we also have a displacement vector. Okay, and this will be important. And what we're going to assume that the cable sags under its own weight, and we're going to assume that there's no motion in the x or y directions. So that means that the cable doesn't swing side to side, because it obviously can't, because this is a two-dimensional model. But if it could, then there would be some additional math we would need to do. So what does our displacement vector actually mean? Our displacement vector actually means that that each point along the cable moves downward amount proportional to x squared, and alpha is just our sag sharpness constant. So basically what it's saying is that it's proportional to x squared. So x squared, this is this thing right here. Obviously, this looks like a parabola, so that means that the points, like all of these points that are on the cable, are decreasing quadratically. And you can kind of see this because you can see that it kind of looks like a parabola a bit. So yeah, that one could also have just been figured out too. So the strain tensor, we're going to want to find the stress that this bridge endures, because this is very important, because, well, this is kind of the whole function of the bridge. It needs to be able to handle a lot of stress. For example, cars or semi-trucks rolling on top of it, and there needs to be able to drive and walk on the bridge freely without fear of it collapsing. So the stress tensor here is going to be an important thing to figure out. But first, we need to find the strain tensor. So the strain of this bridge, which is denoted like this, is simply going to be the symmetric formula. So when we see symmetric, we're usually talking about 1/2. We're talking about our derivative of the displacement vector and the j component plus the I component. And what this basically is it captures how the material deforms in every direction. So in this case, in the I and the j direction. And this is referencing vectors in this case. So only one of our components in this case is non-zero because, remember, we said earlier that the cable does not have x and y movements, or does not have x and y movements. So the only non-zero components of the strain tensor are xz. Let's write that a little more clearly. Xz and zx, because the order obviously does not matter. So in this case, because our bridge exists only on the z and x axis, there's only going to be a certain z and a certain x, and there's not going to be any y movement. So that's how we figured that out. So if we plug everything into this formula, what we're going to get is this is equal to negative alpha x. And you can obviously do this yourself by plugging in the stuff from the top. So for example, that component right there, the negative alpha x, if we move the 2 down when we take the derivative, we get negative 2 alpha x, and then when we divide it by 2, we get negative alpha x. So that's how we got that. And remember, our alpha is just a constant that's the sag sharpness. So this right here, hold on, my thing is being a little annoying. This right here is the shear strain. So the shear strain is negative alpha x. The cable is basically being pulled downward along its length. And of course, this is like also easily provable because, as you can see here, as the cable extends, it goes down. This is all this means. So yes, it is in fact also able to be observed as well. But it's also cool to mathematically see. Okay. Now, let's relate the strain to the stress to find out our stress tensor. So here we have Hooke's law is what we're going to use. So let me actually put Hooke's law on screen. So this is just going to look like our stress tensor is a combination of our volumetric component and our shear component. So here, this is our Kronecker delta. When I and j are equal, then this is equal to 1. But if I and j are not equal, or they're equal to two different things, then that means that it is equal to 0. Okay? And lambda and mu, in this case, are going to be our material constants. They're also known as Lemay parameters as well. And this obviously depends on what material you're using for the cable. So for here, for our Hooke's law, what we're going to do is we're going to use what we know from what we got up here, and we're going to find this stress tensor. So the stress tensor is given by Hooke's law, and we can see here that this component, which is equal to the trace, this is the trace, and since the displacement is only in z and only depends on x, okay, because as you can see up here, we only have x as a variable in our displacement vector, and it only changes in z because the other two are 0. So that's where we got that assumption from. So this means that the trace is equal to 0. So there's no compression. There's no compression that the bridge experiences. And this is also easily observable because it doesn't experience any compression because there's no force acting in the opposite direction in 3 dimensions to actually squeeze the cord or prevent it from moving. For example, wind or stuff like that. So this is also observable as well. So now we can see that our stress is equal to, in this case, this is going to be equal to just, because this is equal to 0, that means that this entire thing cancels out, and we're just left with 2 mu times our strain. So remember that our mu's are constant, our material constant. However, here we need to deal with this because we don't want the stress in terms of the strain. We just want to know what the stress is without having to compute the strain. So the strain here can be represented if we just replace this with our result that we got up here, which is times negative alpha x. This means that our stress is equal to negative 2 mu alpha x. And obviously this means also the same thing, which is also equal to zx. So I should also probably mention that too, because the order does not matter in this case. So this is the simplified version of the stress tensor to one component. So this is just the shear stress. So if you look at it, it increases linearly. So because mu and alpha are just constants, we just have a negative 2 times some number times some number times a constant. That's what tells us it's linear. And that means that the further along the cable you go, the more stress it feels. So the farther out that you go along the cable, so for example, the cable doesn't experience much stress being out here. This is I'd say the minimum of the stress. The maximum of the stress is near the 2 towers because it's holding the most weight. So basically this tells engineers that they need to reinforce the poles depending on how much stress is made here. So it's basically the reasoning behind why the towers of a bridge need to be super strong and durable. And with suspension bridges, usually when they fall down, it's usually because of that. It's usually because their towers failed to manage the load. So now let's find equilibrium for the bridge. This is basically when the bridge functions properly under stress. So the equilibrium equation, which looks like this, is basically an application of Newton's second law, so that the net force must be equal to 0. And the reason we want the net force equal to 0 is, well, if the net force wasn't equal to 0, that means the bridge would start, as you can see here, the stress and the load is facing downward onto the deck. If the deck was experiencing a positive force, then the deck would start cracking and breaking under the pressure. So that obviously wouldn't be good. You wouldn't want to drive on that bridge. So the change in internal stress must exactly balance the external force. So our rho is our density and g is our gravity, gravity constant. So if we just simply plug in what we have, this is going to be the derivative with respect to x of our result from earlier. So that'll be this. Okay, so the derivative of that is going to be equal to -2 mu alpha. And remember that mu and alpha are just constants. And then we're going to subtract rho g. And let's rearrange for alpha to look at the sag of it. So this is going to be equal to 0. And so we basically just said that we use Newton's second law, saying that the net force must be equal to 0. And so we plugged in our information that we'd found earlier, which is this. And then we're now going to set it equal to 0 to find where alpha is equal, where this equation is equal to 0. So if we add rho g on the other side, and then we can divide by -2 mu, we're going to get alpha is equal to -rho g over 2 mu. And so mu in this case, this is our stiffness, and then g is our gravitational acceleration, so that's your 9 meters per second squared, and then your rho is your density. Okay. So this means that the stress is 0 in the middle. It's not experiencing any stress in the middle. And as you can see up here, I mean, yes, this follows our previous findings that the stress is very, very low or at 0 in the middle because it's just a hanging cable. It's not really experiencing any stress. But since the cable has to be hooked to the tower supports, the material experiences the maximum shear stress near the anchors. So that tells engineers that they need to reinforce that because that is where the shear stress is. And if we go back to remember our definitions, this means that this is going to prevent the bridge from cracking or tearing at pressure. So just to recap, the strain comes from our displacement vector that we used. And the stress is linked to strain. We used Hooke's law. I think I spelled Hooke's law wrong, but it's irrelevant. The equilibrium is a solvable physical model. So we found the equilibrium. This is where the net force was equal to 0. And basically this tells us what kind of tensor do we need for the bridge to to actually function. So here we've just used the displacement field and some tensor operations, and we modeled a real-world structure such as a bridge. Obviously, in 2 dimensions, the math would be more complicated in 3 dimensions. If you would like to see a video like that, you can put it down in the comment section. And that's the power of tensor calculus. Anyways, I hope to do more graduate level videos in the future. I do really like doing higher level math. The videos do take a lot more time though, but I will be happy to produce more if y'all want more. So comment down any topics in graduate math, graduate physics that you want to explore. Anyways, I'll see y'all later. and goodbye.